Suppose we repeat a random experiment several times, where each trial is independent with the same distribution. If xi is the outcome of the ith trial, then the expected value of the sum is, by the linearity of the expected value, n times the expected value of the first trial. But what about the variance of the sum? If we use the computing formula for the variance, that's going to require us to find the expected value of the square of the sum minus the square of the expected value of the sum. So we know the expected value of the sum is just n times the expected value of the first trial, so this second term is easy enough to find. But finding the expected value of the square of the sum is going to require finding the expected value of the products for I not equal to j. So let's begin with the easy case. Again, suppose our trials are independent with the same distribution so that the expected value of each trial is the same. And since the xi's are essentially identical, we can just consider the expected value of, say, x1 times x2. So remember, concrete doesn't hurt. Suppose our random variable could either be 1 or 2 with probability 1/3 or 2/3. So let's find the expected value of the product. So let's set up a tree diagram. So our first trial could have outcome either 1 or 2 with probabilities 1/3 or 2/3. And our second trial could have outcomes 1 or 2 with the same probabilities. And so we can find our expected value by multiplying along each branch, and that will give us. Now, while we could just add these numbers together, let's think about them a little bit more systematically. These top two outcomes are really 1 times 1/3, the outcome 1 times 1/3 plus the outcome 2 times 2/3. And likewise, the outcomes along this second branch are really 2 times 2/3 times 1 times 1/3 plus 2 times 2/3. And note that both of these, we can factor out this common factor 1 times 1/3 plus 2 times 2/3, and we get, which is just the product of the expected values. And we can generalize this if our trials are independent. In that case, the expected value of the product is going to be the sum of the product times the probabilities. Our assumption of independence means the probability of the conjunction is going to be the product of the probabilities of the individual outcomes. And we can split this sum to give us the product of the expected values. And so to compute the variance of the sum, we need to find the expected value of the square of the sum. So expanding that out gives us the linearity of expected value allows us to split this. The expected value of the sum of the squares, again, by the linearity of the expected value, that's just going to be n times the expected value of any one of them. If we, again, assume that all the xi's are independent, then twice this sum is going to be, and note there are n choose 2 terms in this sum. And so again, if all the xi's have the same distribution, this is going to give us next, the square of the expected value of the sum. Again, the linearity of expected value allows us to rewrite the inside. And again, assuming all the xi's have the same distribution, that gives us which we can simplify. And so now we can compute the variance, which will be the expected value of the square of the sum minus the square of the expected value of the sum. Replacing each of these, doing a little bit of algebra, both terms now have a factor of n, so we'll remove that factor. And notice that what's left over is just the variance of x1. Consequently, let xi be a random variable corresponding to the ith trial of a random experiment where each trial has the same and independent probability distribution. Then the variance of the sum is n times the variance of any one of them. For example, if we have a 6-sided die and roll it, the expected value of x is 21/6 and the variance is 35/12. Let's find the expected value and variance of the sum of 3 6-sided dice. So the sum corresponds to the random variable. Since the results shown on each die are independent and identically distributed, then the expected value of x1 plus x2 plus x3, well, that's 3 times the expected value of any one of them. And the variance is going to be 3 times the variance of any one of them. It's important to recognize that our formula works in any direction we want it to work. So suppose we roll 6 6-sided dice and let x be the sum. Let's find the expected value of the square. Well, we could compute the expected value of x squared directly. We'd need to compute a lot of probabilities. Instead, we note that if we roll a single die, the expected value of a single die is 21/6 and the variance is 35/12. Since the outcomes on the individual dice are independent and identically distributed, then if we roll 6 dice, the expected value is 6 times the expected value of any one of them, and the variance will be 6 times the variance of any one of them. Our computing formula gives us a relationship between the expected value, the square, and the variance, and so we find